And welcome to video 3 of section 2, optimizing a simple model in pure Theano. In the previous video, we talked about what is Theano, a Python framework for evaluating mathematical expressions that is really popular for deep learning. In this video, we will talk about a simple single-layer mean-square error regression. We will define the optimization problem in Theano. And finally, we will optimize all the parameters efficiently with Theano without needing to move parameters back and forth to the GPU, in case we are using one. If not, this still helps us to avoid moving data unnecessarily within the CPU memory. Here we have our IPython notebook loaded up using the packages we are going to use. We are going to use NumPy and Theano for calculations and Matplotlib for visualization. It uses the same Anaconda environment we defined before. We start by generating random numbers x and two parameters w and b. All the parameters are here. The objective signal here is simply d equals w times x plus b. But during training, our model will only have access to a noisy version of the desired signal given by y equals d plus n. This is to simulate some real environment. Run this cell, and in the next one, we have a visualization of the signals we just generated. The red line is the desired d, and the blue points are the observed y. In Theano, we start by defining two symbolic vectors, x and y. We will use capital letters as a convention to the Theano symbolic variables, and lowercase letters for NumPy arrays. The parameters we want to optimize should be shared variables, because they have to live in memory, either in the CPU or GPU memory. And we want to change them in place to be faster. Here are the parameters we are going to optimize. These values inside here are the values that we initialize these shared variables with. The output of our model is z equals capital W times capital X plus b. This is a symbolic expression. And the cost function is just the mean squared error between our desired signal y and our output z. In this last line, we are putting the parameters that we want to optimize in a list. Okay. With w.getValue, we move the shared variable from Theano to a regular Python array. Here we print just w to show that it is actually a Theano shared variable. To change that value, we have to define a Theano function and pass it an extra updates list. This list contains shared variable new value pairs. In our example, we want the new value of w to be twice the previous one, just for simplicity. Running the cell to compile the function. After compiling this function w, calling it, and getting the value from w again, we see that it is twice the previous value, just as we defined. Here, we use this idea of changing variables in place to optimize the parameters of our model. In this code, we are not exactly using backpropagation, since we only have one layer, but the idea is the same. We calculate the gradients of the cost function, cost, with respect to the parameters w, and we update these parameters using the rule the new value of the previous parameter is just that value minus a step in the direction of the gradient scaled by a learning rate variable. Finally, we compile our function with the appropriate updates, but we have to pass the inputs necessary to calculate these updates. And here we are going to do just that. These necessary inputs are the function actual inputs x and the desired y. Since we have everything to calculate cost in here, we decide to also output it. It is interesting to output the cost function to check if your model is actually improving, if it is actually doing well. If the cost is going lower and lower, this is a good sign. This cell right here is how we can use our compiled function train to update the parameters of our model. These first few lines here are all that we actually need. Just get a pair of input-output patterns and call the train function repeatedly. Here we're going to use the entire dataset at once. For larger datasets, we would use mini batches instead. The main reason for using batches at all instead of one point at a time is to average the stochastic gradient and reduce optimization error. These other lines in the cell are for visualization purposes. Let us run the code and see our model adapting. The first row in this image is the cost function itself. We call this the learning curve. Since we are adapting only two parameters, we can also visualize them in a plane. The start in the middle are the original values, the ones that we want to estimate. These red points are the current values of our adaptive model. See how it approaches the star after every step of the gradient descent optimization. Finally, let's see the final result. Again, these blue points are the observed values, and the line in the middle is what we actually want to estimate. Zooming in this image, we can see that the estimated black line is pretty close to the original red one, although we never saw this red line, only these noisy observations. This algorithm we just trained, a linear model optimized with mean squared error, is actually one of the first ever adaptive methods. All the other neural networks follow the same ideas, but using deep models instead of linear ones, and possibly different cost functions instead of the mean squared error. So make sure you play around with this code and develop your intuition about it. Since everything else that we do will have Theano and parameters being updated in place. This ends our section devoted to understanding what is Theano and how to use it for training adaptive functions. In this section, we talked about an introduction to backpropagation. Afterwards, we talked about Theano, which is one of the most popular ways of doing deep learning with Python. And finally, we wrote a code to optimize a simple model in pure Theano. And then in the next section, we will talk about how Keras makes Theano even easier to use.